All right. So today we're going to wrap up our introduction to relativity, and hopefully by the end of today you'll have enough understanding under your belt such that we can actually do the relativistic treatment of electricity and magnetism. So we'll start that then on Monday next week. So there are a couple of things that I want to talk about. The first is that we never really explained what we mean by contravariant and covariant. And so we need to talk about what we actually mean by contravariant and covariant. So we'll go back to 3D and the metric tensor and the transform that takes you from one coordinate system to the other, which is the Jacobian. And I'll show you what we mean when we say something is contravariant and something is covariant. The other thing we need to talk about is the metric tensor itself. So we dipped our toes in the metric tensor. The metric tensor in Minkowski spacetime is very straightforward. It's just 1 minus 1 minus 1 minus 1, which makes life a lot easier. It's a generalization of the Cartesian coordinate system, right? So you have, orthogonality everywhere. Now in Minkowski spacetime, there is another orthogonality, which is called Minskowski orthogonality, which we will also get into, but that's not what I wanted to talk about. In Cartesian coordinate systems, if you want to know what the length of a vector is, you can just take the x and the y and the z components, square them, add them together, and then you have the total length. And that's because the unit vectors don't really change from one point to the other. Or to put it in another way, the basis vectors don't change as a function of the coordinates for where you are. Now, obviously, that doesn't work for spherical coordinates, right? So spherical coordinates, depending on where you are on the sphere, r is pointing in this direction or in that direction. So if you want to know what the length of a vector is, you cannot just take r, theta, and phi and then square them, not even if you correct for it by slapping on appropriate prefactors. What you actually usually need to do is you'll need to integrate it. So the metric tensor for generalized curvilinear coordinates, so things that are not Cartesian, so that have a non-affine relation, or there are other ways of expressing this, but basically if the coordinates unit vectors change as a function of where you are in space, you can't really do that anymore. So then the metric tensor doesn't actually tell you anything about absolute coordinate differences. It only tells you something about infinitesimal coordinate systems. So I want to formalize that a little bit. So we'll talk about those. And then we got to talk about contra and covariant for vectors when we're talking about relativity. And then, of course, the transform is not the Jacobian matrix, but it is the Lorentz transformation. So I'll show you what we mean by covariant and contravariant. And then we have to talk about differential operators in four vector notation. So we'll talk about the gradient and the divergence and D'Alembertian. I'll show you how to generalize the directional derivative as well. And then we go back to mechanics. So mechanics, we started a little bit in last class. We only did the I think we only did the 4 velocity, and we showed that 4 velocity had a vector of length 1. Now, the fact that 4 velocity has a vector of length 1 actually turns out to be rather important, and I'll try to give you a couple of examples of why the 4 length is an important quantity and immediately expresses certain very important relativistic concepts, such as you can't go faster than the speed of light. Okay, so with that said, any other questions? Okay, let's call this the metric tensor in 3D. So R3 or whatever you want to call it. So if you have a some kind of a vector, let's say we have the position vector, and we're going to write that as some x, y, and z. then our vector length is obviously going to be x squared plus y squared plus z squared, and then the square root. So if you wanted to write that as something ij, xi, xj, where xi and xj are the components of that vector, then that implies that in a Cartesian coordinate system, because there's a 1 here in front and then there's a sign and 1 here, a sign and 1 there. So if you want to know what r squared is, you just need to use the metric tensor, which is gij, which is just 1, 1, 1, easy peasy. And of course, this is why we like using Cartesian coordinate systems, because metric tensor doesn't mess things up. But sometimes certain symmetries require using different coordinate systems. So for instance, we can also define it in terms of, so I'm going to actually, as a function of r, theta and phi. And so now we're talking about spherical. Okay, so spherical coordinates r, which is now a function of r, theta, and phi. In this case, the metric tensor is actually in this form. It's 1 r squared and r squared sine squared theta, such that the length of a vector, there's some redundancy, position, vector, and the coordinates, should be r squared plus, oh, hang on a second. Okay, dl squared. All right, should be dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared, right? So what we did is we took the coordinate vector r theta phi, sorry, dr d theta d phi, and we multiplied that twice, and now we got the length. So the metric tensor basically encodes what is length, right? So this comes here, this comes here. Okay, so this is still 0, this is still 0. But like I was saying, this is something that you usually use for, in non-affine coordinate systems, you have to use the differential form if you want to make sense of the coordinate system. Okay, now, so the coordinates are labeled with an upper index. That implies that it's contravariant. And then the question is, well, contravariant with respect to what exactly? So, so when we were talking about Lorentz transforms, we had some kind of a Lorentz transform that would take you from some system to a prime system. So there's a Lorentz transform. So now we're not doing Lorentz transform. We're just doing general coordinate transforms. So for instance, something that takes you from Cartesian. Oh, let me actually keep that, because so this is the Lorentz transform. So here we have, for instance, a Cartesian coordinates to, let's say, spherical coordinates. Okay, so in that case, we can get, let's call this the primed coordinate system, so x prime, and this is the original coordinate system. Then we can get the coordinates of the primed coordinate system by taking the partial derivative, there's an I here, and there's a J here, and multiply that by xj. And this looks a little funny, but you have seen this before. This is the Jacobian matrix. And sometimes you'll find this, this written as J, I, J, X, J, but be very careful because it's actually, this is not actually a tensor. So it looks like one, but it's not, because it brings you from one coordinate system to another. So that's why we call it the Jacobian matrix. Okay, so that's the thing that takes you from xj to xi. So if we take a very, very simple example, so let's say we go, we have an x-axis, and we go in a new coordinate system where we double the axis, so we just make it 2 times bigger. Then in the 1 dimensions, that Jacobian is just 2. Okay, so that means that the coordinates, and in this case, we have only the 1 coordinate, so that's a prime, that's a 1. It's going to be 2 times whatever the first coordinate was in the non-rescaled coordinate system. Okay, what does that mean? Well, that means that the numbers here are, so the numbers here and the numbers here, 2 times this, hang on, I'm mixing up my, this is a 1. Okay, so if the numbers are 2 times bigger, but they still represent the same physical size, that means that the scale is contravariant, right? So what we call 1 meter in the new coordinate system is therefore ½ a meter. So the Jacobian goes up by a factor 2, but all the physical interpretation of what constitutes a unit length goes down by a factor 2. And that's why it's contravariant. Down. So this is the contravariant definition. Oops. And the covariant definition, oops. X, no, come on, Henk. X prime I would be, of course, lower now. So covariant would go in the opposite direction. Hang on a second, I gotta review my notes. I have it written down somewhere. J, X, and there's an X here. There's gotta be, I think, a J and an I here. And I think this is the primed coordinate system. Check my notes. Yeah, so that's covariant. Yes. Yeah, so another way you could do is you could put an overbar here. So for instance, this is the new coordinate system. So there's the red coordinate system, and this is the old coordinate system. And you see that they are reversed, right? So this is the new coordinate system, and this is the old coordinate system. And you see that that Jacobian is inverted. So blue on top, blue on the bottom. So now on to Lorentz transformations. Okay, so in this case, we had a Lorentz transform where we went from let's say S to S prime with some kind of a Lorentz transform. And then in S prime, the new coordinates would be x prime mu. We're using Greek indices now because mu, remember mu is so 0, 1, 2, 3 because we're adding time, or rather c times time to it. Okay, and we get that by taking the Lorentz transform mu x mu, and this is the Lorentz transform. And for instance, for very straightforward, minus b gamma v gamma. So this is for 1D x speed v. Okay, so that's very, very, very idealized Lorentz transformation, but that's what you get. Okay, so so contravariant in this case means goes with the Lorentz transform like this. So the Lorentz transform is the thing that takes you from a coordinate system x or S to an inertial system S prime. So it does play the same role as the Jacobian matrix, right? Because it takes you from one coordinate system to another, except now we're doing this in 4D. So it plays kind of the same role. Okay, now so if this is contravariant, so if this is contravariant, what is covariant? What does covariant mean? Okay, so let's review that that we had a we wanted to have something that would be an invariant, right? So we have let's say x prime mu. So this is the contravariant, and then that's the covariant form. Hang on, where are my notes? Notes are gone. Here we go. So we know that, let me just do this the other way around. Actually, we know how the contravariant 4-vector transforms because it goes with this Lorentz transform, right? And that will be times x nu. Okay, so that's the first part. So that's this one. Now about the about this one, we don't know yet what that means. So let's call it this thing y or something, and we're going to call this, that's a new new transform, and now we have an x mu here. Now we need to be a little bit careful here because we're doing now a sum over a contravariant, covariant index. So where we place the index is a little bit tricky, but it ends up going here. So sorry. X beta. So this goes here. Let me see, that's beta, and this is mu. So this is this. So think about that. If you calculate this, that's like a dot product, which means one is a row vector, the other is a column vector. So in matrix multiplication, you basically go from right multiplication to left multiplication. So that's why it looks a little funky. So you're adding, you're summing over the first index and not the second index. Okay. Now, if we want this to be, so let me actually change this a little bit, lambda mu nu, and now our new matrix beta mu, and we have an x nu and an x beta. Okay, we want this to be equal to x nu, for instance. Okay, that means that this must be equal to delta beta nu, such that when you stick that in there, you get delta beta nu, x beta, and that is by definition x nu. All right, now that means that y beta mu is the inverse of the Lorentz transform. Okay, so because it is the inverse of the Lorentz transform, when you have a product of something that transforms with the Lorentz transform and something that transforms with the inverse of the transform, in the end, it is independent of the Lorentz transform. And that's why that dot product of x mu is independent of the coordinate system. So it's the inverse of the Lorentz transform, and that means covariant. Okay. And now, finally, if you want to actually see how that works out in terms of vector elements, so remember that in Minkowski spacetime, you have this, right? So the thing that takes you from x mu to x mu is just you go, let's say, from CT R, you go to CT minus R vector. Okay, so all you do when you multiply by the metric tensor in the Minkowski spacetime is flip the spatial part. Okay, so does that translate to having the inverse of the Lorentz transform? Why, yes, it does, because we know that the inverse Lorentz transform is simply changing v to minus v, okay, which is basically the same as flipping the spatial part, right? Remember, we did this last class where we actually calculated the inverse of that Lorentz transformation matrix, and now we see why that is. So covariant means goes with the inverse of the Lorentz transform. Contravariant goes with the regular transform. Invariant means you get something that is independent of the coordinate system that you're in. All right, let's say, so let's do some calculus. Oops. Do some calculus. What is wrong with my writing today? Let's do some calculus today. So if we have a, let's say we have the gradient operator and we have ddt, it makes sense to try to come up with a differential operator that works in Floer spacetime or Minkowski spacetime that combines these two, right? Because we got a spatial part and we've got a temporal part. we can even make it more explicit because we can actually write the, sometimes we do this, we can write the gradient sometimes as, let me actually make a little bit more space. So you write the gradient like this, or d dr vector. And now it's really, really clear that there is a lot of similarities between the differential time and the differential spatial operation. So let's try something. So let's try d dx mu. So d dx mu, I'm using the upper index on the thing that I'm taking the derivative with respect to, because these are your coordinates, right? So these are, you know, t, x, y, z, and those are the ones from the contravariant coordinate system. So it makes sense to keep that index there. Now, that would mean that, okay, we're going to call this ddt and then the gradient. Okay, so let's try what that does. So so first application. The gradient. So for instance, let's say we have some kind of a scalar field. It could be the potential. Now we could, you know, in 3D, we have phi as a function of rho, sorry, r. The gradient of phi r is something. Okay. Now let's see what that gradient does for a 4 vector. So let's say we have a so in Minkowski spacetime, so that's capital M. So this is now a function of the coordinates x mu. So it's a time and space dependent scalar field. So it could be the potential as a function of, you know, due to some moving charge or something. Okay. Now let's see what that divergence does. So for instance, we can, no, sorry, the gradient. Oops. We could let this operator act on our coordinate system. So something like this, and we evaluate it in some position u, and yeah, u. Okay. Now, what happens if we take the gradient and we move move a little bit away from the gradient? Then a Taylor expansion let's say would look like this. So phi at some position u mu plus some distance, let's say w mu. Actually, let me put this down here. Mu w mu would be, well, you start in phi, sorry, in u, and you just add the first derivative and then the dot product with the distance, right? This is your regular derivative, phi, but then evaluated at u mu. Okay, so compare, let's say f of x plus a is f x plus a times f x, oops, plus higher order terms. Okay, so we can also have higher order terms here. Okay, now the scalar potential is a way of labeling or some kind of a scalar field is just a way of labeling points in space. And the labels that we're getting should be independent of the coordinate system that we pick, right? So independent of whether we call something Earth or some kind of a location in the solar system, we can still say what the temperature on at CSUN is, right? So we use different coordinate system, but physically the temperature is not dependent on the coordinate system. Okay, so if it physically does not depend on the coordinate system, then that means that this should be an invariant. So this needs to be an invariant. Okay. And because it needs to be an invariant, we can make that explicit, and we can say, well, if W mu is contravariant, then that operator that we're contracting over we could write as delta mu invariant. So now let me write it as a full thing. So we say U mu plus W mu is starting point U mu plus, this is omega, or W mu del, oh, come on. I'm so used to writing partials. Del mu of phi evaluated at U mu. But it should be obvious now that del mu is covariant. And it is, in this case, ddt and the gradient, or ddt d dr vector. Those are the same notation. All right. So that's the gradient, first application. The second application. The divergence. So remember that if we have some kind of field. So we've got the electric field. Take the divergence, then that's like doing a dot product. We already at some point started writing things like this, but I want to stay away from the electric field for a little bit because we have not really discussed the tensor form of the electric field. So let's just take instead of E, let's take some vector field V. Okay, so that's the divergence. Okay, so what does the divergence do? Divergence in Minkowski spacetime. So let's see. Well, if we have del mu V mu, okay, well, that will be ddt of U0 plus the divergence of the, it's not U, it's V. Come on. V0 plus the regular divergence. So it's a generalization of the divergence. What we will see, for instance, is that when we finally do our E&M, is that if we have, so look ahead, if we use a current 4 vector J mu, which has C rho and the current density as its component, then del mu J mu actually is ddt C rho plus the divergence of J, which is 0 because that's charge conservation. So charge conservation in relativistic form is just that the divergence of this, I'm so used to writing a vector, divergence of this is 0. Couldn't help myself, but that's just super, super pretty. So there's a real use for the divergence in E&M, in relativistic E&M. Okay, so the example 3, they say examples or applications? Okay, application. Well, first, let's call this this is the contravariant differential operator. So remember that G just flips the spatial part. So really all we're doing is we have a ddt here, and now we just took minus the gradient. Okay. So using this one, we can construct this operator, del mu, one upper and one lower. And that's going to be, if you work out the dot product, it's going to be ddt, so it's acting on something, it's going to be d dt squared minus the gradient squared, or the Laplacian. And this we had called the D'Alembertian. And remember where we had the D'Alembertian, we had it in the wave equation, right? We had the D'Alembertian of A, D'Alembertian of J, the D'Alembertian of, A, phi, E, and B. So we have 4 wave equations. So this is the wave equation. The beauty is that this thing, hey, that's a cool marker. Not what I was going for, but okay. That is the D'Alembertian. And it's Lorentz invariant. Now that's a good thing that it's Lorentz invariant, because if we had a wave equation, we really want these waves to, I mean, they might look a little bit differently, but the wave equation for waves of light should be wave equation for waves of light. Okay. Finally, the directional derivative, application 4. The directional derivative. So in 3D, we had, for instance, we had the gradient of some vector field, scalar field. And then if we dotted that with A, then we basically say, okay, how does phi change in the A direction? All right, so the gradient is pointing in some direction, is going to give you some kind of a vector. And then you dot that with the direction, and then you can say exactly, okay, if I walk a certain distance in that direction, how is that scalar quantity going to change? So we sometimes write the directional derivative like this. Okay, so we just group them. So in Minskowski spacetime, we write that as del A of phi, where it is A mu d dx mu of phi, or A mu del mu phi. So it's the same. This is the directional derivative. So see, there is a dot product there, right? So we are evaluating the dot product, and we're going in the direction indicated by that 4 vector a mu. Okay, and in a special case that if you take the velocity, if you take the gradient, that's now the 4 gradient in the direction of u of some function, then that's the same as how that function changes with its proper time. I haven't seen this one myself too much yet, but the book makes mention of it, so I'm sure we will encounter that at some point. Okay. Back to mechanics. So remember that we had the 4 velocity, which we defined as ddt, where this was the proper time of x mu. By the way, I didn't specify. So this is proper time, which is actually it's also an invariant, because even if observers are in different coordinate frames, they can still work backwards and try to figure out how fast the clock is running in some other coordinate system and try to figure out what the proper time in that coordinate system is. Otherwise, this thing would get all messed up. So so we had, for instance, in a co-moving frame, co-moving with the particle, this is just 1, 0, right? Because this is the time, proper time. Oops, time. I'm running out of space, but not out of time. Okay, that was corny, I apologize. So that is time, that is space. All right. So in a co-moving frame, it makes a lot of sense that the 4 velocity would be like that, because time is just running at 1 click a second, and we're stationary in that frame, or the particle's stationary in that frame. And then you do Lorentz transform, and then you get the lab frame. What was it? Gamma V. Yeah. Okay. And we call this thing U, mu. And so we said that U was 1. And because we're writing it as a dot product, it is as a Minskowski dot product, right? So we have a contravariant part and a covariant part. This thing is invariant, and we went through the fact that we went through this, and we said, well, this works out for the in a co-moving frame because it's 1, obviously, as well as the lab frame. When you work out the arithmetic, you get this. So this is an invariant. And the invariant here, because it is bigger than 0, that means that this is time-like. And it means that, and that's consistent with the fact that it could be the world. And it's never like this. So that means, and this is for a particle with mass. So a particle with mass. We don't talk about photons yet. With mass. And because it's bigger than 1, it means that V over C is less than 1, right? So that's what it implies. Because if V was equal to C, then we would have 0, right? Because it would be light-like. And I don't even know what smaller than 0 would be. I guess you'd be on the temporal on the spatial axis. Okay, so let's talk about the 4 acceleration. Okay, let's call that thing W, and let's call that dd tau of u, or so that makes sense, right? So A is ddt of v vector. All right, so we just generalized it. Now, and let me also write this as W mu. Okay. So the question is, I'm going to let you work on this. What is this dot product evaluate to? Okay. Well, this surprised some of you, which I understand. It's not too complicated. You just put in that W, the 4 vector W is the derivative of U with respect to tau. And of course, because of the symmetry of U, you can write that as 1/2 ddt of U dot U, which is 1/2, oops, ddt of, sorry, is just, this is 1, which we had before, so this is 0. And that is important. This is what we call Minskowski orthogonality. What does it mean when 2 4 vectors, in particular, these two are orthogonal? So for instance, in space-time, right, if they're orthogonal, then if this is x and this is t, that means that they are, two different axes on the coordinate system, and even in a co-moving frame, t prime, x prime, the Minkowski dot product would still be 0 because there would still be a time and an x-axis, and that's why you get this skewed coordinate system. But this is obviously something different because this pertains specifically to U and W. So let's translate that back to, let's say we have an A and a V that is, oops, that's not a vector, is 0. What does that mean? Well, it means that there's a force, for instance, that's acting on some kind of an object, and it's giving it a certain acceleration, but the acceleration is not going to change the speed. So A is not going to change the speed, right? Might change the components, but it's not going to change the speed. So famous example, of course, you got a particle going in an orbit. There's some centripetal force that is deflecting it, but the actual speed is not changing. So what does that mean in this case? Well, it means that no matter how much acceleration we're going to give, we're not going to change U, and more importantly, U is always going to stay 1. In other words, once a massive particle going less than the speed of light, always a massive particle going less than the speed of light. Okay, so U dot W is 0 means U is always going to mean length, always going to stay 1, right? We already knew that because we had already established that dot product of U with itself, the Minkowski 4 dot product with itself, was a number that was 1 that was independent of the coordinate system. But now we're seeing that even if we now appropriately define the acceleration, that still works out. So that's what it means when it's 0. Okay, now let's talk about momentum. How are we doing on space? Oh, okay. Let's talk momentum. Okay, so classically we've got this momentum, and we make that out of the vector out of the position vector, sorry, the velocity vector by multiplying with v. Now, we actually have a 4 vector already, p, which was, let me see, it was gamma, and gamma, and now this is big V, okay? Remember that this big V is normalized, so that's actually V over C. So if you want to go from here to there, we need to pick up a factor M and C. So let's put those in. So missing a factor M and a factor C. Okay, so we have P is MCU. So the C is important here, right? You would think that if we have a P vector, then a P4 vector would just also be M times U, but just remember that the 4-speed vector actually has gammas and normalized velocities in it already. So that's why we're picking up an extra factor of C. Now, this is the part where we need to note the following. So this is gamma M C V. This thing actually has units of energy divided by C. So why not, for kicks, and this is where I was saying we're just trying some stuff, let's just call this E. Let's call this thing P. Okay, now we're getting for P the classic, the one that you've seen before. You get the relativistic description of momentum if you write this out: 1 minus v squared over c squared. That's what this evaluates to. Okay. But we also know that in a co-moving frame, come on, P is 0, and gamma is 1. All right, now check this out. If the energy, over C is mc, then that means E is mc squared. Da-da-da. Okay, so we have this property, which in the rest system is mc squared. So C, but there's an extra C. Yes, so it would just be E over C squared. And we can write that as E over C squared minus the classic momentum squared, right? So we have E squared and P squared. So E over C squared, P squared. Okay. And that means that there is a mass energy relation that says that E squared C squared P squared And this is the relativistic mass energy balance. All right, so you have energy that is carried by both the kinetic energy and what we call the rest energy, which is mc squared. Okay. For forces, there are two things from mechanics that we're combining. One is how the energy changes, and the other how the momentum changes when we have a force acting on it. And we put those together in a single object. So using that, the zeroth object of the momentum captures the energy over c. The dE dt being equal to v dot f goes there. And the spatial part is just a regular dp dt is gamma times f. And you get your 4 force. And then finally, if you work out that dot product of u dotted with f in the Minskowski force space, you'll end up getting 0 again, because no matter how big your force, you can't change the length of u. It's always going to be 1. So there you go.